Sir, we are live now. Please start.
I can go to the Zoom, right? YouTube.
Yeah, please open that YouTube for seeing the chat.
Okay. Right, YouTube. Okay, now can you hear me?
Yes, sir, I can hear you clearly. Yeah.
Now we started. Yeah, please tell me when the people have joined. Are there people joining the?
Sir, there are 6 watching on YouTube.
There are 6 people. Okay. 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 Good evening to those who have joined this session, and we will have question and answers regarding our course on Cathodic protection engineering. So please feel free to put in your questions in the chat box, which we can discuss. To start with, there's a question came from one of you regarding the relationship between the current density and the corrosion rate. Now, this answer probably one should look at the basic books on corrosion. In fact, I have a NPTEL course on aqueous corrosion and control. Let me give a brief answer here. The Faraday's law relates the current to the loss in metal in the case of corrosion and the gain in metal in the case of electrodeposition. That means if one passes 1 Faraday current, 96,500 coulombs of current, then the metal loss would be equal to 1 gram equivalent weight. What is this 1 gram equivalent weight? The 1 gram equivalent weight is equal to atomic weight divided by the valency. For example, if it is iron, if its atomic weight is taken approximately as 58, if it corrodes as Fe2 plus, you divide 58 by 2, that will be gram equivalent weight. If it corrodes as Fe3 plus, divide 58 by 3. That becomes the gram equivalent weight. So there is a relationship between the current and the loss in metal in the case of the corrosion rate. Now that is a weight change. Now you have to convert the weight change into the thickness loss, right? So how do you do that? You do it by, you take the weight loss, divide that by density, okay, then you will be able to see the thickness, right? Now, of course, you have to take what is called as a unit area, right? Again, the corrosion rate may be given in terms of millimeter per year. So you have to now take current density, whatever you're observing, multiply by current into seconds, seconds multiplied by minutes, minutes multiplied by the hour multiplied by 24 in a day, and again multiply by 365, that many days in a year. That is the amount of coulombs. The current multiplied by these factors gives you that number of coulombs. So 96,500 coulomb is equal to 1 gram equal in weight. So this much coulombs gives you how much loss in weight. Now loss in weight is known. You know the density, and the current is given in terms of, let's say, ampere per centimeter square. So, okay. So you know, and density is equal to gram per centimeter cube. Now you will able to now, from that, you will able to get, excuse me, the thickness, loss. Okay. I would say that you please take a piece of paper, put them together, and you will able to get that particular one. Okay. From that way, you can able to derive your own equation relating the current density to the thickness loss. That will be a better way of understanding the subject. Okay, I hope you do follow. If you still have some difficulty, please write to me. We'll give you some equation, and you can follow that. Okay, thank you. Is there any other question? Okay. Okay, so there is also a question related to the measured potential of the pipeline. Please look at my lectures a bit more carefully. The corrosion potential or the natural potentials, or we call a open circuit potential, measured on a freely corroding metal. A freely corroding metal means it is not protective cathodically. So when you make a measurement of that particular potential, that corrosion potential is the result of the cathodic kinetics. Maybe like H plus electron gives you hydrogen, or the oxygen can get reduced into hydroxide, and the metal dissolution process. Both the kinetics are there, You have a cathodic kinetics, you have anodic kinetics, and the intersection of these two kinetic line gives you ICAR value. Now, how does this ICAR, how does this ICAR occur? Suppose if the metal is passivating, and if the cathodic potential is very large, then the ICAR value will be higher. Okay. For example, stainless steel. The stainless steel will have higher ICAR compared to the carbon steel. Why? Because it is passivating. Okay. And because it is passivating, and you find that the cathodic curve intersects the anodic curve in the passive region. So the ICAR will be in the passive region, and so the corrosion current is equal to passive current density. So the potential starts moving up. So assume that the same stainless steel is not passivating. If the anodic curve is flat, it goes linearly in the E versus log I curve, then the ICAR will be down. That means the stainless steel, when it doesn't passivate, the E car will be lower, more negative. When it passivates, the E car will be relatively positive. And so, more negative potential means it is corroding more. Less negative potential means it is corroding less because it's passivation. So, now consider for a steel. Assume that the soil has a pH value slightly alkaline in nature. The metal will start passivating. The potential starts, will be start lying in the passive region. So the potential will be relatively positive. And so the metal will start corroding less. So a system which is not subjected to cathodic protection, when the potential is going to be and the more positive direction, it is likely that it is getting passivated actually. Okay. And so the corrosion rate is going to be less. But look at the cathodic protection. Okay. What do you do in cathodic protection? You are suppressing the potential from E car to more negative value. That means, right? You are bringing down the potential to more negative value. That means from E car, when the potential is bringing it down, so automatically the corrosion rate comes down because it is following the same kinetic line. So you need to consider the two cases independently. When it is cathodically protected, a shift in potential towards a more negative value from E car will be lowering the corrosion rate. When it is not subjected to cathodic protection, if a steel has got relatively positive value, is very likely to be in the passive region, and so E car positive means it is lower corrosion rate. So it should be seen from that particular point of view. It cannot be seen just as numbers. Okay, it is very important to understand this particular one. I do hope that you followed that one. And okay, if you still have doubt, you please do let me know, and we can send you a detailed description through email. Okay, thank you very much for the question. Are there any other questions? Anyone would like to have ask any questions? Okay, and I'll wait for another minute. If there are no more questions, we can close down our live interaction session. Well, I think we can, if there are no more questions, let us now close our discussion. Thank you for joining the interactive sessions. Thank you very much.
Okay, so thank you so much. We are closing the session.